before we even talk about what we're talking about today, I'm gonna ask you a question.
Oh boy.
Let's say that I drew, well, I did just draw a right triangle, and let's say that its sides are 4 and 3, and I want to know what is the length of this guy right there. Give you a minute to work that out. You should know the Pythagorean theorem.
Yeah.
Okay, so
Hold on.
I will give you a second to ponder that guy.
Ah. Okay.
Okay, did you get the length?
Pretty sure it's 5.
It is 5. It is 5. Now, what I'm guessing you did is something like this. If we call that side, we know the Pythagorean theorem tells us that if you have a base and a height on a right triangle, then the base squared plus the height squared is equal to the square of the hypotenuse. And so if you're trying to get that C by itself, what you do is you take the square root of both sides, and that gives you that the length that we were looking for. We didn't know that this was 5, should be that thing squared plus that thing squared, and you take the square root. And indeed, that is, that's true, because the square root of that stuff is the square root of 16 plus 9. 16 plus 9 is 25. The square root of 25 is 5. And so, yes, that works. Okay. All right. So we're on the same page. Now, I'm going to ask you one more question. Let's do it this way. Say I drew a triangle, which I just did, and I told you that its lengths were, say, 3 and 4. What is the length of this guy right here?
5.
Are you sure?
Yeah.
Yeah, right. My point. It doesn't matter how you orient this triangle, right? If I take this same triangle, orient it this way, or perhaps if I orient it this way, that length is going to be 5 no matter what. Okay. And length, by the way, is always positive, right? A distance is always, well, usually almost always positive, right? And when I say what is the distance between two things, it's never negative. We're always talking about a positive number. Okay, so how does this tie into what we're talking about today? Well, we're going to be talking about the geometry of complex numbers. And we've talked before that a complex number has 2 components, a real component and an imaginary component. And what mathematicians figured out is that you can consider these 2 components in the following way. We could say, okay, since we have 2 components, we could think about these as 2 different dimensions or 2 different axes. We could say that this horizontal axis is the real axis. And we could say that this vertical axis is the imaginary axis. And given any complex number, a plus ib, we could graph this thing somewhere. And so, for instance, if let's call it z equals, let's do the square root of 3 plus I. We could graph this guy. We could say, well, the square root of 3 is the real part, right? And so the real value that we would go over to would be the square root of 3. And then if we, what's the imaginary value here?
C equals. Hold on.
No problem.
What?
So this complex number right here, what do we, when we have something like this, what is the imaginary value there? Like if it were, let's say 3 plus 2i, we would say the value.
Square root of -1, isn't it?
Well, yeah. We know that. That's that part. What I'm asking is in this guy, what's the b value?
Oh, 1?
1. Yeah. I didn't make it clear, but yeah, that's the, yes, it is a square root of -1. And so what we do is we say, well, you know what? This imaginary line is just like the real line, only instead of going 1, 2, 3, and so on, it goes 1i. It goes 2i and 3i. And then going in the downward direction, instead of counting by ones, we're counting by i's. We're counting by -1i, -2i, -3i's. And we make the I the same length as 1 on the real axis. And as a matter of fact, I is sometimes called the imaginary unit. And 1 is called the real unit, right? Unit, we could go really in depth why, like what's special about that, but you could think about it as a unit of measurement, right? We're measuring the reals by a unit of 1. We're measuring the imaginaries by a unit of I. So we have 1i, 2i, 3i, and so forth. So if we wanted to graph this guy, where this z lives on the, this is called the complex plane, we would say it's right here. We go over that real value, which is the square root of 3, and we go up 1 unit, which would take us to right here. And now what we're going to do is say, well, here's something to notice, is that there's a distance from here to the origin. What distance is that? Well, let's think about this. This guy is just a triangle, right? What's the base? How long is the base of that triangle?
Square root of 3?
Square root of 3. What's the height of the triangle?
I?
Yeah, but we're talking about distances now.
1i?
Well, it's just 1. The distance is just 1. Like, yes, and yeah, I see what you're saying. Yes, but we are thinking about this just in terms of length. And yeah, I kind of see. Yeah, and so like I said, we measure up and down in terms of I, but when we're actually talking about distance, we're just thinking about, if I were to draw a triangle, that length, like I said before, we're measuring off in terms of I, but that length is the same length as from there to there, which is 1. And so we're going to say that triangle, forgetting now that we're calling this the imaginary axis. If we were just calling this x, yeah, that's Kayla.
Peter.
Just the imaginary, if we forget then that we're talking about the imaginary part of it, and we're just thinking about the XY plane, we would say then that has a height of 1. And therefore, what is the length of the hypotenuse?
Three square. Oh, hold on.
Whoa.
Isn't it just gonna be the square root of 3?
Well,
Well, because the square root of, wow, okay. 3 squared is just 3.
3. And then what's that guy squared?
Oh, whoops. I forgot the plus. Right. Plus
All right.
1. And then, so 4 square root of 4 is equal to c, which is 2.
There we go. That length right there should just be 2. Okay. And that, so it doesn't matter where you are in the complex plane. This is why I made this point earlier. Like if I would have drawn this going down, right? Like in the same kind of orientation that I did before, where now, let's say we're at, let's do it this way. Well, actually, doesn't matter where we draw it. If I had drawn it, say, this way, where we're down here at negative root 3 and up here at positive I, well, we can see that's exactly the same length. It's got to be 2. And indeed, if we had the complex number negative root 3 plus I, and we wanted to find the distance of that point right here from the origin, we'd say, well, it doesn't matter that you're calling this negative. This is just a length. And that length is root 3. And so you have a triangle with the root 3 as the length there. You still have a height of 1. And so we end up in the exact same place where we say, oh, well, that right there is 2. Now let's get real tricky. Let's say I was down here at minus 1 and minus root 3. This is not drawn very well, but you can imagine that, right? If we're here at the real value minus 1 minus I times root 3, that would be this guy right here. Our triangle would look a little bit different. It would look something like this. But the distance, again, even though that's a minus 1, we're just talking about the length here. So that guy would be a length of positive 1, because like I was saying at the beginning, we always think of length as a positive number. The height of that triangle would be, well, I guess we're going down root 3 units. And so it's just root 3. Again, we have the exact same triangle. It's just oriented a little bit differently. The hypotenuse is still going to be 2 right there. Okay. So, okay, where are we going with this? Well, we have this idea, well, of measurement. One way of measuring a point in the plane is to see how far away from the origin it is. That is the straight line distance from the origin. Can I erase this stuff right here?
Yeah.
Okay. And so your book defines it as absolute value of a complex number. That nobody calls it that. I don't. Your book does. We call it the magnitude of a complex number. Or modulus. Magnitude or modulus. Magnitude of a complex number. A plus IB is the distance from origin to the point A comma B. And so thinking about this, in the complex plane, you have your real axis, you have your imaginary axis, and we have a given complex number, A plus IB. And we've done a couple examples now. We're just going to pretend that A is right here, that B is right here. Then that is the point, A plus IB, which you'll notice corresponds exactly to what we've been doing all along. Like there's a one-to-one correspondence between this point, which we're considering as one number now, and the pair of points A comma B. And so it's kind of like the same thing if I say, what's the magnitude of this complex number? I'm really asking the same question as, what's the distance from the point A comma B to the origin? And while we've already done this, but to really drive the point home is that this side of this right triangle is A, has length A. The length of the height of this right triangle is B, and therefore the distance is just the square root of A squared plus B squared, right there. So let me know when you got all that.
I'm good.
Okay, does this make sense?
Mm-hmm.
This is not a new concept. It's just we're kind of playing with. The only thing new about this is we're saying this is, we're going to consider this thing as one number, but it's pretty obvious to see that, like, well, wait, this, if you're drawing this way, where the I part just tells you how high up or down to go, it's really the same thing as points in the plane that we've been dealing with for years now. And really, there's no well, there's a little bit of difference that's going to show up in just a second. But when we're talking about distance, there's nothing new here. So let's do.
Wait, hold on a second.
Say what?
1 second, actually.
Okay.
I had to read it. Here, and then that is.
Okay, so there is a shorthand way of writing this, and we use absolute value bars. A plus IB, the absolute value of, and that's why your book calls it the absolute value, but we're not going to do that. We're going to call it magnitude. The magnitude of a complex number, A plus IB, is the square root of A squared plus B squared, which is the distance from the origin to that point on the plane. Now, let's just check for understanding here. I'm going to give you one to do. What is the magnitude of the complex number? 3 minus 4i.
That's going to be -3 squared plus a -4 squared. 9 16, or the square root of that is 5, and then 5, I think.
There it is, right? And now if we think about this geometrically, what we have is a point on the plane. Where is that point? Well, you go over that way 3 units. You go down that way 4 units, and you're here at the point -3, -4. Or minus 3 minus 4i means the same thing. And you're asking what's the distance from there to there? And all we've done really is we've just constructed this triangle, right? That triangle has one side is 3, the other side is 4. And so what do you know? All those negatives never really mattered, did they? You just take whatever number that is and you square it. It's always going to be positive. You take whatever number and square it. Well, it's always going to be positive. And so this all kind of works out, right? Like, it doesn't matter which way you orient your triangle. The distances are always going to be positive. Always going to get that. So there will, yeah. So in your homework, you are going to have to graph a couple of complex numbers, like this one that I just did right there. That one is right there. You're also going to have to find the magnitude of some complex numbers. They call it absolute value. It's the magnitude. One more thing we do need to talk about on this, though, is now, let's say we're given something like, so do you feel comfortable with all this so far?
Yeah.
Okay. One last thing in that section, this is section 7-8, is you might see something like this: the set of A plus IB such that, and then some kinds of restrictions on A and B. So you might have something like this, where A is less than 2 and B is, let's say, greater than or equal to 3. You're given this set and you're told to graph that set. Well, we know that this corresponds to the real value. The A is the real value. The real value is the horizontal axis. The vertical is the imaginary, and so this value B is the imaginary one. And so this says that A has to be strictly less than positive 2. And so everything over here, and so we've done this before, that would be not including that line right there, and everything on the left-hand side of it. B has to be bigger than or equal to 3, so I'll put a 3 right there and a dark line. And then where both of those guys intersect, where both of them are true, would be this area right here. One tricky thing though. So this is, you've seen this before. Instead of just saying the set of x comma y such that x is less than 2 and y is bigger than or equal to 3, that's the exact same thing as this. It's just that now we're going to consider x values to be real values, y values to be the imaginary component there. So it's just, there's nothing really new there. This is a little tricky though. Let's say I did the same thing. Sorry, I just went and erased that. I didn't bother to ask if you had.
We're good.
Good, okay. So now let's do this. We want to graph the set of complex numbers such that their magnitude is equal to 1. We're talking about the distance from the origin. Let's think about that, right? This just means the distance from the origin out is equal to 1. What is this object? Something that's the same distance to a point.
What?
So this is an object, a mathematical object, and it's the set of all points that are equidistant to a central point.
Circle?
It's a circle. Exactly. Exactly. So in this case, this circle would be centered at the origin, and it would have radius 1. So it would go through 1. It would go through -1. It would go through I up here. It would also go through -I down here. And this thing would look just like well, that's not quite a circle, but it would be just a circle, right? It would be all points whose whose magnitude is equal to 1. That's that right there. If I said less than or equal to 1, then I would be talking about the interior of this guy right here. That would be a nice way of saying, well, if its absolute value is less than or equal to 1, it's everything that's inside that circle right there. And so that's really all there is to section 7-8. Any questions before we move into uncharted territory?
Hold on.
Mhm.
No.
Okay, cool. So really, long story short, the complex plane is almost exactly like, at least when it comes to graphing and distances and stuff like that, it's almost exactly like our old friend R2. I'm not sure if I ever called it R2, but R2, which is just our XY plane that we've been dealing with for years now, and we're really familiar with. Any point in that plane, say here at A and B, we call the point A comma B. With the complex plane looks like that. We're saying, oh, wait a second, it's the same thing, only we're going to call this point A plus IB. And we are now including this nifty thing, I, which has the property that I squared is equal to -1. So, okay. So another thing, what else can we do with complex numbers? So the conjugate of a complex number. You remember earlier when we had something like this. And we wanted to rationalize the denominator. And the problem was we can't, if we tried to just multiply by square root of 2 times the square root of 3, we are still going to have roots in the denominator. And so what did we have to do? What did we have to multiply this guy by in order to kill all the roots?
Multiply by that bottom. No, wait, no. Wait, the conjugate, right?
The conjugate, exactly. And what is it? How do I write that?
Well, it's the same thing, but a minus instead of a plus.
There you go. Right, and so we do that right there. The top is just multiplied by 1, so it just works out to this. And then this is the whole point of this, is that the first gives me what? First multiplication?
2.
The outer and the inner do what?
Cancel.
They cancel out every single time. In fact, we don't really need to use our brains for that, right? Like that's why we did it. The reason why we flipped the sign was so that the outer and the inner will be exactly the same, but with opposite sides, so they will cancel out. And then what do we get with the last multiplication?
3.
Positive or negative?
Minus.
Minus. And in this case, it's always minus, because the signs are different, right? That's why, that's all part of it, right? So if this one had been a negative, we would have written a positive here, and it would still have worked out this way. because the negative and the positive would have made a negative, blah, 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 blah. And that's how we dealt with that. Okay. The conjugate of a complex number is exactly the same. Given a complex number, a plus bi, its conjugate is, what is it? What is the conjugate of a plus bi?
A minus that.
There you go.
Ib.
There you go. It's that simple. So, for instance, 2 minus 3i, what's its conjugate?
Two plus 3i.
2 plus 3i. Let's see what happens when I multiply them by each other. What do I get for my first multiplication?
4.
4. What do my outer and my inner do?
Cancel.
They cancel out. We don't need to use our brains for that one. I mean, but if we wanted to, we could. We could say 2 times 3i would be 6i. Negative 3i times 2 would be negative 6i. Oh yeah, the outer and the inner cancel. And then what do I get for my last multiplication?
Minus 9. And then I squared is minus 1.
And
So it
so
would just be plus 9.
there we go. And so we end up with 4 plus 9 right there. Notice that this is always going to happen the same way as before. When we multiplied the last, it always gave us a negative because they have opposite signs. This is always going to happen when you multiply conjugates. They're always going to have different signs. So you're always going to have negative, whatever that thing is squared, times I squared, which is always -1, which always makes that positive. Now let's do another one real quick. I want to take a complex number and multiply it by its conjugate. Let's use, how about, don't want to do that. Yeah, let's do it. 3 plus 4i. And I want to multiply it by its conjugate. What is the conjugate of this bad boy?
3 minus 4i.
All right. First, outer, inner, last gives me what?
9.
Mm-hmm.
Plus 16. Or I guess.
Yeah, plus 16, right? And the way that you got that was negative times a negative, negative times a positive is a negative. So minus 16i squared, which we said is minus 16 times a -1, which is a 9 plus 16, which is what? It's 9 plus 16.
25.
Does this look familiar? Do these numbers look familiar to you?
Yeah.
Yeah, it was like what we've been doing this whole class, right? If you have the number 3 plus 4i, then that's that point right there. And it turns out that if you multiply it by its conjugate, it gives you the distance squared. Another way of talking about the magnitude of a complex number is to say, you take your complex number, multiply it by its conjugate, and then take the square root of that, and you will get the distance. That's always going to be true. Let's kind of prove that that's always true for any number. Can I erase this right here?
Yeah.
Okay. So same kind of picture. If I have a plus ib and I multiply it by its conjugate, a minus ib, what do I get? Well, first gives me what?
A squared.
The outer and the inner do what?
Cancel.
They cancel, leaving me with what for my last?
Plus b squared.
Which, hey, what do you know? We just said that the absolute, I keep saying it now, that the magnitude of a complex number is equal to a squared plus b squared, whatever the components are squared, and you take the square root. Well, that's the same thing as the square root of the conjugates. And at this point in your mathematical career, this is not necessary to talk about, really. It's kind of there's a there are a few subtle reasons why it's good to know this. For our purposes right now, it's not pressing, but it's just something to notice that this is going to happen. So another thing to notice is when we were trying to say rationalize a denominator, we multiplied something with square roots in it by its conjugate, and it gave us pure, in our case, integers or numbers or something like that without their square roots. This is the same idea going on here. If we want to get rid of something with an I in it, multiply it by its conjugate, and you will be left with a pure real number. There's no i's left over here. You have, in effect, a distance or a squared distance. So that's going to be useful. That's going to be very useful. That's where, in fact, we're going with all of this. Okay, so we didn't state this. Can I get rid of this stuff?
Yeah.
Okay, we didn't state this explicitly. I just kind of went along with it, but to multiply two complex numbers, we do it the same way we've done it anytime we've seen something like this. We go first, outer, inner, last. In this case, our first gives us a 6. Our outside gives us a minus 8i. Our inner gives us a plus 3i. And our last gives us a negative 4i squared, which we can simplify by saying 6 minus 8i plus 3i. That's a negative 1. A negative is a positive. And so positive 4. 6 plus 4 is 10. 3 minus 8 is minus 5, so minus 5i. That's how we multiply two complex numbers. Not much to it. You're just, the only new thing is that now I squared we rewrite as negative 1. But you could have figured that one out. So now, okay, we've talked about conjugates. We've talked about multiplying these guys. Now, let's do this. My motivating example for all of this was we had something like this, 1 over square root of 2 plus square root of 3, and we wanted to rationalize the denominator. Well, let's do something similar here. Let's say instead of square root of 2 plus square root of 3, let's just say we have, let's use actual numbers. How about 2 minus 3i? Now, instead of saying rationalize the denominator, what we want to do here is this is a complex number, but we like to write our complex numbers in this form right here, where we have a real number plus, so whatever it turns out to be, it might be really ugly, plus I times some other number. Why? Well, partially because of geometry. If we know that A is, say, 7, and we know that B is 5, we could plot this on the plane and say, then 7 plus 5i lives right here, and that gives us some kind of insight into our problem. This right here, where does he live? I have no idea. I honestly have no idea where this guy lives. I cannot plot this right here. If somebody gave this to me and said, graph this on the complex plane, the SOL. So let's, knowing that a conjugate can kill this guy off, let's get rid of the imaginary part there in the denominator by doing the same thing. Just by analogy with what we did before, right? I know that if I multiply this guy by his conjugate, it's going to get rid of the I. And so the only way to do that and not change the number is to multiply it by 1. And so what do I need to write in here?
2 plus 3r.
And what goes in the numerator?
Everything.
The exact same thing. It has to. Otherwise, I've just changed everything. And so now, okay. I'm just going to go ahead and just take care of the numerator in one fell swoop because that's easy, right? 1 times a number is just whatever that number is. So we have 2 plus 3i. Now the denominator comes out to what?
All right. 4
Yep.
plus 9.
I think 4 plus 9. Well, let's just double check, right? First gives me 4. Outer, inner, I could see cancel, so I don't need to worry about it. -3 times 3 is -9, but you have the I squared, which makes it a +9. So yes, there we go. Okay, so let's simplify this a little bit. We have 2 plus 3i on the top, and 4 plus 9 is what?
13.
13. Now we're not quite in that form. I still can't really graph this the way that it is. But what I could do is just split this up. I have one denominator and a sum on top. And so here, I'm going to even copy this down again to make the point. Say, this is the same thing as splitting this up. That's 2/13 plus 3/13 I. Or, and really, I guess what I'm doing here is saying, like, there's my I, right? And you end up with 3i over 13. But that last step that I'm doing is just saying, oh yeah, well, that right there is the same as this, because that's the form I'm looking for, right? And I just like to see it visually like that. If you were to write 3i over 13, you're absolutely right. It's just, when I look at this, this tells me, that's my X point right there. That's my Y point right there. And so then if I were to graph this guy, I'd say, he's right here. He's at, well, I don't know, I guess 2/13 is right here. And 3/13 is right here. And so that's where that guy lives, right there. And that is actually this original point right there. So that 1 divided by 2 minus 3i lives right there, because he is actually equal to this number right there. Does that make sense? So that's pretty much all we're doing with that kind of stuff. You'll be given things like this, and it'll say multiply or divide. And, well, this is what it means to do. Like, rewrite this given thing in this form right there. Okay. Now, another one they'll say is express the reciprocal in this form. and they'll give you something like this. They'll say, express the reciprocal of this in this form. This is what they mean to do. The reciprocal of a number is just 1 over that number. And so you say, okay, the reciprocal of this is 1 over 2 minus 3i. I need to rewrite this in this form. I know this nifty trick that turns the denominator into a real number. And so you do this trick and you end up right there. Okay? Okay. This is where it's a little tricky. Now, one more thing. The reciprocal of negative I. What's the reciprocal of negative I? Oh, it's not equal. Don't think about it. If I told you what's the reciprocal of B, you would say it's something. I just heard static.
1 over I.
1 over negative I, right? And the reciprocal of negative I. Okay, so that's that. But again, where does that live? I don't know. I can't graph that. So we could be creative here if you want. We don't, like you could multiply the top and the bottom by anything you want. And just notice, like, if the reciprocal of something is you make the imaginary part negative, and if it's negative, you make it positive, you could say, well, negative I is equal to 0 minus I. So its reciprocal would be 0 plus I. 0 plus I. And so you could say, well, we could just move along with the reciprocal here and just say, well, then 0 plus I is the reciprocal of that guy. And so then we have an I on top. Negative I times I, which is negative I squared. Negative I squared is negative 1. And so finally, that's just an I. Okay, so there's no difference there. It's just a little tricky because I by itself is 0 plus I. So yeah, but okay, so that's not too bad. But what about this bad boy right here? Can I erase this stuff?
Yeah.
Okay. Before we do this, if I did this, n to the negative 7 equals what? How would I rewrite that without a negative exponent?
1 over n to the 7th.
There we go, right? Because whenever I see a negative exponent, I know that means take me to the other side of a divide sign and make me positive. So what is I to the negative 7?
1 over I to the 7th.
1 over I to the 7th. Now at this point, you might go, oh, I need to multiply by a reciprocal. Yeah, if you wanted to like make your life really hard, you could try to figure this out. Or you could say, hold up. There's that thing about I, right? Is like every time you get a fourth one, it goes back to 1, right? I squared is negative 1, I to the 3rd is negative I to the 4th is 1, which means I to the 5th is I. Then to the 6th would be negative 1. To the 7th would be negative I. Oh, I just need one more I to turn that guy into a number I could deal with. And so in this case, I would say, well, just multiply this guy by I,
Yes.
top and bottom, and we end up with an I in the top and then an I to the 8th in the bottom, which we can reduce any way you want. I love how you did some in the homework, you did different ways of doing this. I just happen to know that I to the 8th is 1, and so we have I over 1, leaving me with just I, and so I to the negative 7 is equal to right there.
I know, but we would bring
So that's some stuff you'll see in the homework. One last thing I want to talk about. And yeah, wow, we're actually doing really well on time. This never happens. So, okay, good with this one?
Mm-hmm.
Okay. The last thing I want to talk about is, I think it's your last problem too, is you're given something like this and you're told to express in the form. Yeah, that's expressed in the form A plus BI. And this is what they give you. And that is a minus. Okay, you got that?
Yeah.
Okay, so we don't want to just, well, there's a few ways of doing this. There is a few ways we could do this. I think the easiest way is, since I know that I could multiply by a conjugate, multiply a complex number by its conjugate to turn it into a real number and get that denominator to be a pure real number, then I could just do that trick where I just split up the top and the bottom, or split up the real part from the imaginary part in the numerator. Problem is this guy right here. It's hard to see what the conjugate of this is. It turns out to be equal to 1 plus I squared, but we don't want to go down that road. Trust me on this, we don't want to go down that road right now. It's going to be much easier to just say, well, why don't I first express this in this form? That is, get it, just multiply it out, and then I'll just flip the sign in the middle. It'll be easier to do that way. So let's do that. And if you want to play with it, you could do it another way. But what I'm going to do, what I'm going to suggest, is that we first just square this bad boy out and see what we get. And then it'll be easier to find its conjugate. And so, what do we get? First, outer, inner, last.
1.
Uh-huh.
And then minus I.
Uh-huh.
Minus I.
Uh-huh.
And then I squared.
Plus I squared. Yeah. And then the way I like to do sign, just in my head, do signs first and go negative times negative is a positive, a positive. Then I go I and I is I squared. Okay. So now let's simplify this a little bit. 1 minus I. Well, that I squared, I'm going to rewrite as negative 1. I see we have a 1 minus a 1. That's nice. But 1 minus 1 is gone, and now I just have minus I, which is minus, why don't we write it as minus 2I? Okay. Now again, are you here? Do you buy this? Do you believe this? Okay. Okay, all we did was just squared that out and got it into that form. Now, if we wanted to, we could think about this as this is 0 minus 2i. And so its reciprocal would be 0 plus 2i. And then first, outer, inner, last would give me a negative 4i squared or a positive 4. That's perfectly fine. We could do it that way. In fact, I want to drive this point home. Let's do it that way. Let's multiply the top and the bottom by its reciprocal. And so the reciprocal of minus 2i is plus 2i. So I'm going to do the top and the bottom by plus 2i. The bottom I already gave that away. We have negative 4i squared, which makes it a positive 4. What do we get on the top?
Um, 2i plus 2i squared.
Okay. So that is, how would I rewrite this with my real and then imaginary?
I'm not sure.
Okay. Well, what is I squared?
Minus I?
Wait,
No, so whoa, hold on. Sorry. No. Minus 1.
Okay. So then that 2i is actually, or I'm sorry, that 2i squared is actually just negative 2, right? So in other words, well, 2i minus 2. Okay. It's almost in the correct form. It's just we usually write our i's in the second place. So I'm going to go ahead and do this. How about negative 2 plus 2i all over 4. Almost there. We just need to split up the denominator. So this splits up into, how about negative 2 over 4 plus 2 over 4 times I. Check me on that. Make sure I did that right.
Yeah.
Which reduces to what?
Negative 1/2. Plus 1/2 I.
There you go. Now you could graph this thing, right? If we wanted to, we can see where on the complex plane that guy lives. Now, watch this. Because I was saying earlier, like, we could just multiply this thing by its reciprocal. And that's almost always going to be the way that you do it. Can I erase the work that we've done here?
Yeah.
Okay. The interesting thing to notice here is that, well, first off, I don't have, in this case, I don't have the problem of, so like, well, 4, when our denominator was something like this, root 2 plus root 3, well, then we needed to multiply by a reciprocal because we couldn't get rid of both of them without doing that, right? But if my denominator were just this guy right here, what would I need to multiply by to get rid of this square root 3 in the denominator?
Square root of 3.
Square root 3, exactly. We wouldn't need to go overkill, right? Because there's just one thing to kill. And we wouldn't need to go to square root 3 either. It's just the square root 3 is the thing that we need to kill. And so in this case, we happen to have just a pure imaginary thing. And we could get rid of that bad boy right there by multiplying by what?
I.
Just I. I is all we need. And it's almost the exact same thing, right? I mean, like, if you look at this problem, this happens to be the square root of 3. Well, that's just the square root of something. And so we don't need to go above and beyond to kill it. But but I wanted to go through the long, hard way to show you that even if you just blindly say, you know what, I'm just going to multiply by the reciprocal, it's going to work and you're going to get to the right answer. But if you notice, wait a second, I don't need to go through all that and just do this, let's see what happens. So in the bottom, what's negative 2i times I?
-2i squared.
Negative 2i squared, which is what?
Just 2, isn't it?
Positive 2, yeah, because that's negative 2 times negative 1 is just a positive 2. So positive 2. Now in the numerator, let's see what we get. We're going to have to distribute that I, and what do we get?
1. So -1. Wait, stop. Whoa. Sorry. Would you? Oh my goodness. I. I plus I squared.
There we go. And what's I squared?
Minus I. -1.
-1. Now we normally write it, it's telling us to express it in this form. So let's get the reals on the left and the imaginaries on the right. And so that gives us what? Just in the numerator here. How do we write that?
One. Yeah.
Well, it's -1 plus I.
That's I.
Just doing the opposite order, because this is a plus I and that's a -1. In fact, we did that just a second ago when it was 2's, right? I think we ended up with 2i minus 2 in the numerator and said, well, let's flip it around so that it's in this form here. And so we put our reals up front, and they just bring along with them whatever sign is in front of them. And so that's the same thing as a -1 plus I. Same way, like, and think if we want to think about I as just a variable, if we had x minus 1, for whatever reason, we might want to rewrite that as -1 plus x, but they both mean the same thing, right? And so in this case, I do want to write it that way because I'm trying to get my thing to look like this. I'm trying to group all of my reals on one side and all of my imaginaries on the other side. So that's why I chose to write it that way. And then we can see that if you were to then split this bad boy up, which is what we're supposed to do, we're supposed to get that a by itself. Well, to do that, we say that's -1/2 plus 1/2, or I over 2, which is 1/2 I, which is the exact same thing we got the other way. My point is, I guess you end up doing about the same amount of work. It's just, we don't need to go overkill down here and do the full 2 times I, because then we're just going to have to factor out a 2, or when we divide, we ended up last time with -2/4 over, or sorry, -2/4 plus 2/4 I, and then had to do that. But either way you do it, right, you will get to the exact same answer once you have reduced your final A and B here.
Mm-hmm.
And so another thing to notice is that in this case, this is in the form A plus BI, where A is equal to -1/2 and B is equal to 1/2. So, okay, that is all for today. Are you ready for your homework assignment?
Yeah.
Okie dokie. So, gonna look ugly because we covered 2 different sections, and I'm giving you parts 1 and parts 2 in each section. So let's organize it this way. From chapter 7, section 8, you'll have a part 1 and a part 2. And from chapter 7, section 9, you will have a part 1 and a part 2. So 7, 8, part 1 is just numbers 1 and 7. Part 2 is 3, 5, 11. 13, 15. Section 9, part 1. 7.9, part 1 is 913. 1929. Part 2. Seven, 11, 15, 17, 21. 25, 27. 31 and 33. I believe this is a total of 20. And just to be clear, part 1, these are both due Thursday at 8. That's both of these part 1s. Thursday at 8. Both of the part 2s are due Friday